All right, so to introduce Washington Mio, who will be speaking to us on stable local homology metric measure spaces.
Okay, thank you, Peter, for inviting me to give a talk. Slides. I'm going to be speaking with joint work with my former student, Mao Li. She's now at a plant research center in St. Louis. Mehmet Akhtar, who's a current FSC student, and also Facundo Memoli at Ohio State. First slide, I want to show a few of the problems that motivated this kind of work on these lines. So for example, suppose you have looking at a particular phenotypic trait, say the shape of the leaf of a plant, or it could be a root system. And one very important question is to understand the genetic basis of variation of particular traits. And if you don't know anything about what genes, for example, may be implicated in such variation, you typically run an initial exploratory study that it pretty much goes along the following lines. So you're looking at shape of leaves, and you collect a large collection of leaves, and somehow you have to quantify the variation. Now you see the genome, and then you look at the variation in genotype, and then you start to look at possible correlations. Now, when you see high correlations, you have candidate genes that may be implicated in a particular phenotypic traits. Now, biologists have all kinds of tricks once you have these candidate genes, or how to try to go beyond correlation and actually try to establish a more correlation. I may say a few words about that in a second. Right? So, some association between genes and phenotypic traits is one of the problems, but there are similar questions where instead of looking at phenotypic genotypic variation, you may be looking at differences in environmental conditions. For example, suppose there's variation in temperature in the environment or CO2 level in the atmosphere, and then does that do anything to some particular phenotypic traits? Right. So this example that I have here, you see the head of a duck. This is an embryonic duck. So this is, suppose say that in a preliminary study you identify some candidate gene. Then you start to look at, and if that gene encodes, say, some particular protein, at some particular time in development, you may start to look at expression of that protein. Then you may ask similar questions. So in green, you see the region where a particular protein, in this case, sonic hedgehog, is being expressed. Then we'll normally look at the level of expression and try to associate that to genotypic variation. But also these days, they're starting to look at the shape of these expression domains. And you see that these shapes typically are very irregular. So there's no very obvious way of doing that. So now, the biological problems aside, what kind of technical issues you run into? Well, typically, I'm going to assume that the data, the phenotypic data, especially shape, is collected in the form of a point cloud. Right? So many times you do a lot of pre-processing on these point clouds, but each time you do this, if you want to provide a theoretical basis for what you're doing, it becomes harder and harder to justify that things are robust and sound. So I'm going to try to minimize the assumptions and just assume that our phenotypic data or shape data is collected as a collection of point clouds and try to and somehow capture the geometry of those particular objects in some way. Well, a few other remarks that I wanted to make from the right now is that, for example, if you look at the shape of the leaf that I have, the very first shape, you see that there's the global shape. Now there's a lot of shape characteristics that occur at a smaller spatial scales. For example, there are lobes that occur at certain scales, at a much smaller scales, hysteretions, and all of these things are important both functionally and for various reasons. Right? So another question is related to what I'm going to be speaking today. This is a problem I've been talking quite a bit with Ezra Miller at Duke. If you observe the topology and geometry of a shape and say that you observe that at a particular scale, to make that more precise later. Now you can ask the question, so you don't have the full shape, but you can observe, you can sample the shape at the endpoints. The question becomes, how densely I have to observe, I have to sample a shape if I want to pick up a particular topological geometric structure. So what I'm going to try to, the point of this talk is that you can capture a lot of geometry through localized topology. So I'm going to try to make this point a little clearer on the next slide. And I'm going to start with the Euclidean data, but also ask similar questions for points and more general spaces. Right? So just to try to make this point that local topology is able to capture a lot of geometry more clear, let me start with very simple remarks. The classical stability theorem says that if you have two continuous functions, say defined on the compact polyhedron, you do level set persistence. The bottleneck distance between the resulting diagrams is bounded by the L infinity distance between the original functions. But let's look there instead of a stability statement the other way, right? So think bottleneck distance as a lower bound for the infinity distance between the functions that somehow, let's say, is capturing some kind of shape property. Right. Now, instead of looking only at G, compute G with an arbitrary homeomorphism of the domain. Right? If I do persistence over G composed with H, of course, the persistence diagram is going to be the same because a set for one is going to be a homeomorphic image of the level set for the other. So this is a remark that's made explicitly in a recent paper by Fréchet. So because of this, you can actually state an easy consequence of the stability theorem is that the bottleneck distance of the original persistence diagrams is actually less than or equal to the infimum over all homeomorphism of F minus G composed H. You see that you're trying to capture differences between F and H. This is indicating that just the global persistence diagrams, it could be a pretty weak to look at. Right? So let's try to turn things around. Instead of modifying the right side, let's keep the right side fixed, F minus G, and change the persistence diagram. So one simple way of doing this is to take functions and just restrict to a subset of the domain, say a compact polyhedron. Now compute the persistence diagrams of the functions restricted to that. Now the stability theorem implies that the distance between the diagrams of the restricted functions is less than or equal to the L infinity distance between F and G. So you can take the soup over all possible subsets, possible subpolyhedra, and conclude that the supremum of all those bottleneck distances is still less than or equal to the difference between F and G. Right? So as a matter of fact, you can easily recover the full L infinity distance by simply restricting to making K a point. So just take the point where the maximum difference between F and G is achieved. Right? And if you compute the H0 diagram, you see that the bottom distance is exactly that. So this is a pretty, I think, solid indication is that if we can take our initial point cloud, convert into functions that carry a lot of information about the point cloud, then through localization, we should be able to recover topologically a lot of the geometry of the original data sets. Right? So how I'm going to be viewing a point cloud? I'm going to be thinking of a point cloud as random draws from fixed distribution alpha that typically we don't know. From the empirical measure from these observations and think of the empirical measure as a first course approximation to the unknown probability distribution alpha. And I do this more generally on a Borel metric space equipped with the Borel probability measure. So I'm going to first focus on data in Euclidean space, talk about how is it that we can talk about local homology at a fixed scale in a stable manner, and see what happens as we vary scale. And I'm going to say a few words about this type of situation in more general metric spaces. And if I have time, I'll talk about one application. Right? So I'm going to first transform our data set into a function. Right? There's a very classical way of doing this through, say, density estimators. So to simplify things, let's just look at Gaussian density estimators. So let's start with the Gaussian center at the origin, and let's say that the variance is 2t. So t, I'm going to think of the parameter t as my scale parameter. Right? So if I have a Borel probability measure, I'm going to just convolve my measure with that Gaussian and get a smooth representation of that. So I can think of as smoothing or the relaxation of my original measure. So this gives an approximation of the original measure as a measure that has a smooth density, and the density is exactly alpha t. Right? If you do this when you have alpha is the empirical measure, what you get is the usual Gaussian density estimator of band t. Right? So just a remark here, alpha t is well known that this is simply the time t solution of the heat equation. Part t equals Laplacian u with the initial condition, the probability measure, alpha. Right? Example. Suppose that the contour of leaf represented by a few points, and say that I have a few outliers and a little bit of noise. So now if I do a density estimator, I get something like the function that you see on the right side. So you see that now the density estimator is able to downplay the outliers. You see very short peaks there, and the taller peaks are exactly around the contour, except that there are some higher peaks, and those are exactly places where you see a little more ornamentation because there's more concentration of data around those points. So essentially what I'd like to do is to say, let's do super level persistence on alpha t. Right? So that gives essentially my homology of alpha at COT. But it's better in some ways to phrase this in a slightly different way. So before I do this, I'd like to reinterpret alpha t, which is the relaxation of alpha at time t. So let's draw the notion of diffusion distance on Euclidean space. That is in the paper by Hoffman and Lafon in a much broader context. And how is this distance defined? So you fix a scale parameter t, a positive number t, and how you define the t distance between x1 and x2. Well, you replace x1 with a Gaussian of bandwidth t centered at x1, and you do the same to x2. So how you view these two functions as functions in L2, and you just measure the L2 distance. And this 1 over square root 2 is just a factor that's going to be convenient to have later. Right? So now one thing that this does is to turn RD into a space of finite diameter. And it's an easy calculation that the diameter of the space with metric is 1 over 8 pi t raised to the power g over 4. The Fréchet function of alpha on a metric space. Right? So if you have a distribution, a probability measure, so the Fréchet function at a point x essentially measures the spread of the data around that x with respect to the given metric. you look at the distance from every point y, the reference point x, the square distance, and average that out over the distribution. So this is just the expected value of distance squared to the reference point. Notice that for VT, I'm using the diffusion distance at tier 2. This is also just a technical convenience to define some expressions. So now if you do a calculation, you can compute this Fréchet function explicitly. It turns out that it's just a constant minus the original alpha t. This constant is exactly the maximum possible value that t may have. That's independent of alpha. Essentially what it has, we had peak in alpha t where there was concentration of data. Now we flip the sign of alpha and we shifted by this constant to ensure that the function is always positive. So essentially the tall peaks are big values now. So we just essentially flip the function, keeping it positive. So now let me do the first version of localization. So now suppose I have a compact polyhedron. Polyhedron, I just mean a topological triangulable space. Right? So I'm going to find the homology of alpha at scale t, localized to that particular polygon. Persistent homology of the sublevel set filtration of K of the polyhedron via the Fréchet function restricted to that. Right? So I can do this for any dimension I. So for I-dimensional homology, for a scale, and for a fixed polyhedron, I get a persistent diagram or a barcode. I think when you start with data, one of the mostly used constructions is to do persistence of the scale parameter. So we're not doing that here. The scale is fixed. So the parameter is really the height. It's really the height of alpha t, which has to do with mass density. So it's really a probability mass density parameter that they're using to do persistence. So now I'd like to talk about stability of this.
Sorry, Victor, can I interrupt you?
Yes.
So you mentioned super level set persistence on the density function.
Right.
And so you're doing sublevel set persistence on the Fréchet function.
That's right.
When did you switch from sublevel sets?
Oh, the peaks of alpha t become values of the flip of Fréchet function.
Okay.
Okay.
So it was minus.
Yeah.
Alpha t.
Right.
Okay.
Okay. So now, if you want to address stability, what is that? We want to say if I perturb my data somehow, the diagrams don't get perturbed very much. So I need to find ways of measuring perturbation of data. But theoretically, data for me is a probability measure. Right? So we need metrics on the probability measure, but metrics that small variations under that metric are tolerant to some level of noise and some outliers. Otherwise, that doesn't reflect into real robustness of the homological invariance. So it turns out that the Wasserstein metric is a metric with such properties. So I'm going to spend a couple of slides reviewing the definition of the Wasserstein metric. Let's fix larger or equal to 1. So let's only look at distributions with finite pth moment. That is, the integral of x to the p over distribution is finite. Right? So now I have two such distributions. The Wasserstein metric essentially is going to be a measure of how hard it is to reshape alpha into beta. So say that alpha is my vertical distribution in the picture, and beta is the horizontal one. Right? So how is it I can try to reshape alpha into beta? Well, I take math on the ice pile of alpha. I can distribute the way I like on the piles in beta. All right. So the only constraints that I have is that if I add the total amount of mass in the air. Horizontally, I get the total amount of mass in the ice pile alpha, and similarly for vertical piles. Right? So that's the only restriction that I need to impose. That's what's called a coupling. So formally, a transportation plan or a coupling between two probability measures, alpha and beta, is done by a measure of probability on the product space such that if I marginalize in one direction, I recover alpha. If I marginalize in the other direction, I recover beta. So these are all possible ways of reshaping alpha into beta. So let's call gamma alpha beta the set of all such couplings. Right? So now what's the energy of a particular coupling, a particular proposal of changing alpha to beta? That's where P is going to come in. So now, if I move mass from a point Y to a point X, the distance travel is form of Y minus X. So say that the energy spent is that distance raised to the power P. So now if I integrate over the coupling, I get the total energy spent. Right? So the Wasserstein metric is essentially the root of that energy, except that you don't look at one particular coupling, but look at the optimal one. So you optimize over all particular couplings. So a theorem is the following, is that you have two probability measures. Suppose I have finite first moments, so I can talk about the first Wasser W1 of alpha and beta. Right? Then the bottleneck distance between the ith dimensional homology diagrams for alpha and beta at scale T and fixed compact polyhedron K is less or equal to this Lipschitz constant times the W1 distance. And as the Lipschitz constant is depends only on scale. It's independent of K. Right? So one immediate of this is that if I think of W1, a measure of the difference between the geometry of alpha and beta, so I can take the supremum over all polyhedra, and this gives me lower bounds for W1 of alpha and beta. So this is a direct corollary of the stability theorem. Another consequence is the following consistency result that says that suppose now I look at samples. Right? I'm going to draw independent samples that are distributed according to a fixed distribution alpha that typically I don't know. Right? Now I look at the diagram associated with the empirical measure, almost surely that diagram converges to the diagram of the real distribution alpha. Right, so this is a corollary of stability theorem. This is an asymptotic result, right? So you wonder, what do they say? Let's sample at level n. How am I doing in terms of estimating real diagram of alpha? Question of rate of convergence. So in the corollary, we say that things are converging almost surely, but at what rate? Right. So now let's fix, say, a phase n. Say that I look at random draws, independent draws. Right? Then so let's look at the bottleneck distance between the persistence from the empirical measures from real diagram that I don't really know. Right? We can't say anything about diagrams, but let's look at the expected value over all possible such draws. Right? Then this is less than or equal to, there is this constant that doesn't, constant in the denominator here involves only the scale parameter t. This is a constant that's coming from the stability theorem, but there is a complete result with the by Fournier and Guilin that they result on how fast the empiricals converge to the real distribution in Wasserstein distance. And that's where these other constants come from. This constant beta that depends only on the dimension, and M3 that has to do with the third moment of the distribution alpha. Right? And this is multiplied by something that involves the sample size. Right? And the dependence on the sample size is going to depend on the dimension. So we have different expressions for different dimensions. So in low dimensions, dimension 1 and 2, you see that it's essentially n2 minus 1/2, except they have this logarithm in dimension 2. And the dominant term in higher dimensions is 1 over d, minus 1 and minus 1 over d. So this has some relationship with that question that I was mentioning at the beginning of how well you have to sample a distribution if you are trying to capture some particular homological feature they detect at some particular scale. So say you have the diagram, one of the bars of di of alpha represents that particular feature that you're interested in. So if this bar is long enough as compared to the constant on the right-hand side, then it's likely that you expect that samplings will carry a bar of similar nature. So that can be interpreted as a result along those lines. So here's a little experiment.
If you go to your first corollary of validity, so before this one and then before that one, yep. So the second corollary on the bottom of the slide is also an equality if you choose. Can you use some k to make this an equality like you could in the normal stability?
Yeah, the problem there, the thing that here I have Wasserstein of the original distribution instead of L infinity, alpha t and beta t. If I had t beta t, I could push to equality, but if I insist on keeping Wasserstein of alpha and beta, then I don't think I can.
Okay.
Let's run a little experiment. So we start with a single circle. Let's take the uniform measure according to arc length. All right? So now instead of take a single one, take 2 copies of that. So you have 2 forms on 2 joint circles, and now let's take a mixture of these. But on the first circle than on the second. So you have a much heavier circle on the left. Right? Try to sample this distribution. So if you do say n equals 10, you have 5 examples of the sort of thing that you may get. Right? So you see that you hardly see the second circle that has very little mass. Sometimes you see an attempt to form the circle on the left. This from the standpoint of H1. From the standpoint of H0, you see a good scatter of points, depending on the scale that you observe in the data. Right? So you go to n equals 100. So this first circle, the circle on the left looks a lot solid now, but depending on the scale, you may not see the circle on the right so well formed. But you also see that now you see probably fewer connected components on the right circle as well. Right? If as compared to n equals 10. If I go to n equals 1,000, both circles seem to be pretty well formed, and now they are definitely pretty solid when you go to 10,000 points. Right? So it's very hard to see differences between 1,000 and 10,000 here, or if you can see a little plotting the Fréchet functions. So let's plot the Fréchet functions instead of this. So here the scale is 0.03, right? And my polyhedron is just a large rectangle containing all of the data. So if you plot the Fréchet function, you see that, for example, for n equals 10, blue means very low values, so you have very deep valleys there, right? That represent valleys, but shallower valleys. Right? And so you see the evolution as you as your sample size. So now let's take a peek at the persistence diagrams and what you see. So the blue here, we off the parameter. Because the Fréchet function, the maximum value that it attains is 1 over 4 pi t to the power d over 4. We chopped up power d over 2. We are running up to that scale value. So we're not going to see infinite bars here. But one of these dots is actually what would represent an infinite bar if it didn't do it. Right? So blue in this diagram represents H0 and red represents H1. Right? As expected, for n equals 10, you see a large number of connected components, even at that scale. And you hardly see any H1. The H1 that you see is something very close to diagonal. That probably has nothing to do really with those circles, but it's more local little loop that, that's how it's created. Okay. So now when you go to n equals 100, you see that there's one circle that's a little more, shows up more reliably. That's the circle on the left that has more probability mass. Maybe go back to that. So see that the circle on the left is better formed than the circle on the right. Right? And now see a second circle that's because the mass, you have less mass on the right circle, the Fréchet function, the d, the shallower. So you see a circle that doesn't persist as long. N equals 1,000, you see better that circles are already fairly stable, and they're definitely stable when you go to 10,000. So just to get a better sense of what's going on, we took all these diagrams. Here I'm just showing 5 samples for each sample size. We actually did an experiment with 25 samples for each sample size. Right? So we did an MDS multidimensional scaling plot for the H0 data, right? Comparing pairwise bottleneck distances, and that's what you see for H0. Right? You see that for H0 you see a big scatter here. The blue represents n equals 10, and as the sample size increases, things start to converge, and essentially reaching a limit when n gets to 10,000. And similarly, we have a plot for the H1 homology. So for the blue, you see that the right circles, sometimes we saw a little bit, even for n equals 10. This is probably the 3 dots that are close to the blue. The other blue dots are just saying, for those samples, we didn't see any H1. Right? And for the circle, the greens most of the time see the circle on the left, and then red guys start to see a little bit of the circle on the right, and you definitely see both when you get to black, which is a large sample size. Right? So I think that's very consistent with what we did before, but this gives perhaps a better visualization of kind of the phase transition behavior that you observe as the sample size changes. All right. Fix both the scale and the polyhedron K. Right? So now let's vary scale. Well, when you do this, you think of, well, now I have a second persistence parameter, so perhaps I have to do persistence over 2 parameters. But remember that we already have a stability result at a fixed scale, so we don't really need to do this as a second parameter. So we're going to take a different approach. So because for each t, we have a stable diagram, we're going to just, at every t, we're going to think of this as a path in diagram space, right? So let's go dB. This is the space of all persistence diagrams with the bottleneck distance. And as I let my parameter t vary on the interval 0 and infinity, I'm going to get a whole family of persistent diagrams. So that's the path that I call it HK alpha. K is still fixed here. Right? And just by the continuity of solutions of the heat equation, it's not difficult to show that this path is actually continuous. So what do you have now? For each, forget K, K is fixed. For each alpha, I have a path. Now this is diagram space. Let's call path D the space of all such continuous paths. Right? Now I'm going to topologize that with a compact open topology. Right? Compact sets in 0 infinity, open sets in diagram space. Just means in terms of sequences, this is just uniform convergence on compact sets. Right. So I have a Borel measure with finite first moment. I can define the following. Right. So for each measure, let's P1 the space of all Borel measures with finite first moment. For each such measure, I have now a path in diagram space. Right? So now I have topologies on both spaces. Right? So on the I'm looking at the Wasserstein 1, and in path space, I'm looking at the compact open topology. And a consequence of this stability theorem is that the choice of path is continuous now. This is a continuous function on alpha. So illustration of this path. This is just a simple illustration. We just took 5 handwritten digit 1s and 5 handwritten 8s, right? So they are here automatically. So what compact set we took? So first, compute centroid of each one of these point clouds, and we took a fixed ring of at the centroids. So that's my compact set K. So now we computed for each one of these 10 digits, we computed at the path of Eason's diagram space. So now we discretize that path, right? And we did MDS to the entire data set. Right? So these are the projections of the path. So now you see the scale variance. So for example, it's very interesting to what kind of thing you see when you vary scale, for example. So if number 8 intersects that ring, the 2 of the connected components are closer than the 2s, right? If I take 2 in the same horizontal level, they're farther apart than the 2 connected components in vertical direction. So what they're saying is that at some scales, the vertical clusters are going to merge in H0, whereas the horizontal clusters are still going to be different. So you see that through a lot of variation in scale, you start to pick up more geometry of the data, even in this very simple situation.
So to clarify here, in this example, so K is fixed here, and it's the angle that's centered on a center of the
right.
digit.
H0 is essentially doing, if you forget all these technicalities that we went through, is essentially counting the number of connected components of your section. Except that you allow me scale. So if you want to think in the old way, just do some enlargements of that connected components. Right? That's really what's being done in the functional approach. But the only difference is that this is done in a stable way now. So if the scale is large enough, but not too large, what happens? Some connected components of the number 8 are going to merge, but some are not. So then you're going to be able to see the jump from, as you increase the scale, there's going to be a jump from 4 connected components to 2 connected components. And that's encoded in this path. So we want to now issue that I wanted to bring up is what if I vary K now? Right? Well, not vary K. Well, sometimes you want to vary K in an organized way, but sometimes you don't have a real good principle for it. So I like to consider random variations on the polyhedron K to which I'm restricting the data. Right? So to analyze that, it's simpler to do with the following variant of localization. Instead of doing hard localization by restricting the Fréchet function to polyhedron, let's instead take a modulating function K. Right? I'm going to take a function K, define a whole domain, and this function K is only going to be allowed to take values between 0 and 1. Right? Think of K as attributing weights to data at the point X. So here's one example. Let's look at the picture at the bottom. Right? So if I wanted to highlight, say, this disk, what K would be? It would be a function that's essentially 1 on the disk and decays quickly to 0 outside the disk. Similarly for the annulus. Right? So that's a softer way of localizing things through modulation. So what do I mean by that? So instead of restricting, do hard restriction to a subset K, let's multiply the original alpha T, the original density estimator, by this modulating function. Right. Now, as it before, let's flip things. All right, so take the same constant and subtract the modulated function. Now the sub-level set persistence filtration and define localization in this form. Because of the restrictions that we impose on K, the very same stability results holds for this variant of localization. One advantage of that is that now the diagram, if I perturb K in the L infinity norm or the compact open topology, it turns out the diagram vary continuously in the bottleneck distance. So I have continuity on K as well of the diagram. Right? Let's look at the space of all our equations, and I'm going to put the compact open topology there, compact uniform convergence on compact sets. Right? So I want to randomize my localization domain. In other words, let's randomize K. So this is just a measure map from some probability space to the space of allowable weight functions. Right? I could let T vary, but just to simplify things, let's fix T. Right? T and alpha, we can define the following function. Now, for each modulating function K, look at the persistent diagram for alpha at that scale for a particular modulating function K. Right? So now this function is continuous. So if I look at the following composition, so I have the random choice, which is given by the map on my probability space to the weights. Now, for functions, I map that to the persistence diagrams once I fix alpha. So for each alpha, what am I getting? I'm getting now a random diagram in space. Right? Diagram for each choice of K. So what does that mean? That means that I have a Borel measure now of space of diagrams. So that measure nu of alpha and T. Looking at one particular diagram for fixed K, right? And fix alpha and fix T. Let's randomizing K, so that becomes a distribution of diagrams in diagram space. So I have one such distribution for each Borel alpha with first moments. Now, what if I have two of them, right? Distribution for a second measure beta. Sorry, these two things, right? How is this construction stable? Is the distribution for alpha somehow related to the distribution to beta? So let's introduce a way of measuring the difference, the distance between these two distributions. Right? So let's recall the Levy-Prokhorov distance between two Borel. It doesn't need to be probability, but let's stick to that. Measures on a mixed space XD. All right, so this is defined as follows. Each measurable set you look at, and given an epsilon, you take the measurable set A and see the size of that with respect to the first measure. Now enlarge the measurable set by epsilon, look at the epsilon open neighborhood, and look at the size of that with respect to the other measure, and make sure that that result is satisfied, and in the other direction. So look at the infimum of enlargements, so the infimum over epsilon, and that is the Prokhorov distance. Right. So another consequence of the stability theorem is that if I start with two measures in P1 for a fixed, say, G, here is random. Yeah, I shouldn't have fixed K. Right? Then the measures new data, the Prokhorov distance between them, is bounded by the very same constant that I had before times W1 of alpha and beta. Right? So you see that the distributions are also close. Right. So now I only talked about Euclidean space, but I'm kind of running out of time. So I just say a few things of what you can do in more metric space. Well, if you want to mimic the multi-scale model that uses the Gaussian kernel here, right, you do more generally on metric spaces equipped with the diffusion kernel, just like Kaufman and Lafont do. Right? And remember that to talk about diffusion, you need a base measure. So there's a measure new there that here is playing the role of the Lebesgue measuring. This has nothing to do with what I called alpha before. Right? So what are nice examples of this type of setting? Well, there are lots of examples, but for example, on zero or cat K spaces, there are very nice diffusion kernels constructed by Sturm that are generalization of the ordinary hit kernel, but these diffusion kernels can be defined much broader generality, and many of the results can be extended to this type of setting. Right. Another setting is this. Let's forget completely about diffusion. Right? Now, suppose you just have a metric space and a probability measure. So in this setting, you don't have a multi-scale analog. You can still talk about Fréchet functions. For example, if you look at the literature of data on Riemann manifolds, for example, what first thing that people try to do, for example, Bhattacharya and Patranjanari studied quite a bit, is the mean. What do you mean by the mean of such distributions, alpha? These are mean sets, right? And what can you say about such statistics? Well, how is it that the mean is defined? Well, it's again the Fréchet function. You have a metric, so given any x, you look at the spread of the data about that point x. And the mean is the set, the collection of points that minimize this. But these things are very hard not only to analyze in general, because they are sets, but to compute. Right? So how is it that you're going to minimize such a function? But it turns out that if instead of just looking at the mean, you could say, let's look at the whole profile of the Fréchet function. Perhaps I get even more interesting information from that. Right? So compute the persistence diagram of that. Right? And just as before, instead of just computing the global persistence diagram, you can restrict to any polyhedron contained in your domain. And here's a theorem that you can prove is that if you do that, if you have two such distributions, the bottleneck distance between the corresponding persistence diagrams for I-dimensional homology is less than or equal to, this time the Lipschitz constant is 2 times the diameter of your max space. We are assuming that the metric space here is compact, right? Multiplied by the Wasserstein 1 distance. So I had here a few illustrations and an application, but I think are just out of time. So I'm going to stop here and say thank you.
All right, thank you, Washington. So do we have questions for Washington? Maybe to start, can you, so the theory is really beautiful. This could be applied for computations. So for example, the symbol sets of these Fréchet functions, I think, could probably be really complicated, even if we restrict them to kind of compact polyhedra. Is that right?
Yeah, right now there is a serious computational issue in hard dimensions. And so 2D or 2 and 3D domains we can do, right? But as soon as you go to the domain of the function becomes high dimensional, it becomes almost a very difficult proposition. And that's why at the moment, instead of using this to analyze structure of data sets in very high dimensions, we mostly apply to different features of shapes. For example, if you have a leaf in 2D, or if you have a face in 3D space represented by a map, then you can still restrict to polyhedra in those domains, and those are computable because you can compute persistence diagrams in a fairly efficient way. But I think the a more long-term hope here is that much in the philosophy of this low-dimensional structure and high-dimensional data is that even if you are in very high dimensions, many times you're going to be confined into some low-dimensional space. So perhaps there is a way of producing polyhedra that will capture the main topology of the distribution. But I think, so how does that relate more directly to alpha? We are essentially saying perhaps a lot of times distribution alpha is going to be supported near in the vicinity of some low-dimensional complex. So if you can somehow identify that complex, then I think this may become a little more doable. But at this point, we don't have any results in that direction.
Wondering if you could go to the slide about the Levy-Prokhorov notion, the notion of distance between probably on a metric space. Is that right?
That's
right. So one question is, epsilon is playing 2 roles. Epsilon is the offset of A, right? And then it's also the distance between the measure of A according to nu1 and the measure of the offset of A according to nu2. So if you things like if you so you replace D with 2D, for example, it's all understood how that changes pi.
You what?
If you double the metric, meaning the distance between any 2 points is twice what it was before.
Yeah.
Right. You're changing the offsets now. The offsets are changed. Measures have not changed at all.
Right.
I was just I've seen this before, and you could say a bit more about it.
Because it's an epsilon over 2, right?
Notions of distances between measures on probability on metric spaces.
Yeah. Wasserstein, for example.
So Wasserstein is this Earth movers metric. Here you have the definition for me, but is there to think about besides the definition?
Of what?
No, of the Levy Prokhorov.
Yeah. What, you want to see an alternative way of interpreting this? Or
One you can, sure.
one is that, for example, if you have on Polish spaces, for example, this metrizes weak convergence of measures.
I see.
Yeah.
Oh, sorry, I think I muted myself. Yeah, ask just a quick question. So the persistence diagram of the sublevel sets of the Fréchet function are the same as the diagram of the superlevel sets of the kernel density estimator?
Yeah.
Is it just a matter of preference that you like looking at Fréchet function, or is there some?
Well, I think the Fréchet function tells us how to extend that when you don't have the notion, when you don't have the setup to do density estimation, for example.
I see, where you have the metric.
But another interesting point that in the last, suppose, for example, you can do this on a graph. I think that's the simplest situation, right? Suppose you have a distribution on the vertex set of a weighted graph. Now the uniform distribution, same for every node. If you do diffusion, because you have a constant function, nothing happens to the function, right? So the first function, the density estimator is just the analog of the density estimator is just always a constant function, so you don't get any information. But if you do the Fréchet function respect to the diffusion distance, now you do get because what we had before was that constant minus t, but it turns out that constant on a graph, on a weighted graph, is no longer a constant. It's something that depends on the geometry of the graph. Now, even for the constant distribution, you start to see interesting things.
All right. Thank you again for a really nice talk. Thank you.